Hello everybody. In this video we begin with Chapter 9, Vectors, Lines, and Planes. Specifically Section 9.1, Vectors from a Geometric Viewpoint. In this section we are going to consider a three-dimensional coordinate system in which points are determined by ordered triplets. We construct the coordinate system in the following manner. Choose three mutually perpendicular axes, as you can see here in Figure 9.1. That's going to be our system of reference. The orientation of the system is right-handed in the sense that if you hold your right hand so that the fingers curl from the positive x-axis towards the positive y-axis, your thumb points along the z-axis, as you can see here in Figure 9.2. Looking at it from a different perspective, if you are looking straight at the system, the YZ plane is facing you. The XZ plane, which is this one here in orange, is perpendicular to it and extending out of the page towards you. The XY plane is the bottom part of that picture. The XY, XZ, and YZ planes are known as the coordinate planes. Points in space are assigned coordinates in the same manner as in the plane. So point P here in Figure 9.3 is assigned with the triplet XYZ to indicate that it is X, Y, and Z units from the YZ, the XZ, and the XY planes, respectively. So vectors can be represented geometrically by arrows in two- or three-dimensional space. The direction of the arrow specifies the direction of the vector, and the length of the arrow describes what is called its magnitude. The first point in the arrow is called the initial point of the vector. So we have a vector that looks like this. This would be the initial point, and the tip is called the terminal point. So this is the initial point, and this is the terminal. We will denote vectors in lowercase bold italic type. For example, V is a very commonly used letter when assigning a name to a vector. We could also use AB with the arrow indicating the initial point A and the terminal point B. If the initial point of a vector is at the origin, let's say that this one here, this vector here is at the origin. Notice that this is known as a vector in the standard position, also known as a position vector of point P. The terminal point, as you see here, point P, has coordinates x, y, z. We would call these coordinates the components of V. And if we wanted to write this in vectorial form, we would say that V is equal to x, y, and z. Now notice that sometimes vectors are also written in a horizontal way. The length or the magnitude of a vector is known as the modulus or norm. So the modulus or norm, and is denoted by the absolute value of V. The magnitude of a vector is equal to the square root of x squared plus y squared plus z squared. Now notice that if we take into account this triangle that you see here, so this would be the base of the triangle, and this would be the height, as you can see, z. So notice that from Pythagoras, we know that the length of OP squared is equal to OB squared plus BP squared. But we know that OB from here, OB squared, is going to equal x squared plus y squared. Why? Well, because this leg of this other right triangle is x, and this one is y. So we can see clearly that OB squared is equal to x squared plus y squared. And also we have that BP squared is the same as z squared. Therefore, the modulus of V is going to be the square root of x squared plus y squared plus z squared. Now, if you take a look at figure 9.4, two vectors such as V and AB are equal or equivalent if they have the same length or magnitude and the same direction. We would write this as V is equal to vector AB. Geometrically, two vectors are equal if they are translations of one another, as you can see here in figure 9.4. In figure 9.5, we see four vectors that are equal, although they are in different positions. Because vectors are not affected by translations, the initial point of a vector v can be moved to any convenient position by making an appropriate translation. You can see that vector v has its initial point at the origin, which is something very convenient, as we are going to see later. Two vectors are said to be opposite, as you can see here in figure 9.6, if they have the same modulus, but opposite direction. So notice that this would be vector v, and this is vector minus v, with equal modulus or magnitude, but opposite direction. Next, we're going to take a look at addition and subtraction of vectors. According to the triangular rule, if u and v are vectors, then the sum of u plus v is going to be the vector from the initial point of u to the terminal point of v when the vectors are positioned so that the initial point of v is the terminal point of u, as you can see here in figure 9.7. Equivalently, u plus v is also the diagonal, as you can see here in figure 9.8, of the parallelogram whose sides are u and v. Then we have that the difference of two vectors u and v can be dealt with in the same manner. So the vector w, which is equal to u minus v, is a vector such that u is equal to v plus w. In figure 9.9, we see that the difference is along the diagonal joining the two terminal points of the vectors and in the direction v to u. If k is a real positive number, then k times u is a vector of magnitude k times the modulus of u, and in the same direction as u. It follows that when k is negative, k times u has a magnitude of the absolute value of k times the magnitude of u, and is the opposite in direction to u. This is also the condition for two vectors to be parallel, as we can see in figure 9.10. So two vectors are parallel if one vector is a scalar multiple of the other. Here's an example. The vector minus 3, 4, minus 2 is parallel to the vector 4.5 minus 6, 3, since we have this equality. In other words, this vector is a scalar multiple of the other. Components provide a simple way to perform several algebraic operations on vectors. First, by definition, we know that two vectors are equal if they have the same length and the same magnitude. So if we choose to draw the two equal vectors u and v from the origin, then their terminal points must coincide, and hence u1 equals v1, u2 equals v2, and u3 equals v3. So we showed that equal vectors have the same components. The converse is also true. That is, if u1 equals v1, u2 equals v2, and u3 equals v3, then the two vectors are equal. The following results are also obvious from the simple geometry of similar figures. If u equals this and v equals this, and k is any real number, then the sum of u plus v is simply going to be the sum of their components. And likewise, if you have k times the vector u, this is just going to equal k times each of the components of vector u. If the initial point of a vector is not at the origin, then we can generalize the previous notation to any position. If AB is a vector with initial point A and terminal point B, then AB is going to equal OB. This would be a vector from the origin to B, minus OA, a vector from the origin to A. So all we would need to do is subtract the components of OB minus the components of OA. As illustrated in the diagram above, either by applying the distance formula or by using the equality of vectors V and AB, the modulus of vector AB, or the magnitude of vector AB, is going to equal the square root of the difference in x squared plus a difference in y squared plus a difference in z squared. Additionally, the following properties can easily follow from some properties of real numbers. So we have the commutative property of addition, the associative property of addition, and the distributive property of addition. So next we're going to do example 9.1, and it says, given the points A, minus 2, 3, 5, and B, 1, 0, negative 4, part A, find the components of vector AB. So remember that we said that this is the same as vector OB minus vector OA. And since we have the components, this is just going to be 1 minus negative 2, and then we would have 0 minus 3, and negative 4 minus 5. So notice that we're going to get the vector 3, negative 3, and negative 9. For part B, it says find the components of vector BA. So this is just the opposite of vector AB. In other words, vector BA is going to be negative 3, 3, and 9. For part C, it says find the components of 3 times AB. So that's just multiplying the components of AB times 3. So notice then that 3 times vector AB is going to be 9, negative 9, and negative 27. For D, it says find the components of vector OA plus vector OB. So this would just be the sum of vectors OA and OB. In other words, adding the components of the vectors, right? So this would be the same as negative 2 plus 1, 3 plus 0, and 5 plus negative 4. So we're going to get negative 1, 3, 1. For part E, it says calculate the modulus of vector AB and the modulus of vector BA. Now, one thing to notice here is that these two are equal. The magnitude of AB is equal to the magnitude of vector BA, because although they are opposite in direction, they must have the same magnitude. So notice that this is simply going to be 3 squared. So 3 squared plus negative 3 squared plus negative 9 squared. And this is going to give us the square root of 9 plus 9 plus 81. And in the end, we're going to get 3 square root of 11. For f, they want us to calculate the magnitude of 3 times the vector AB. Notice that this is the same as saying 3 times the magnitude of vector AB. So simply 3 times 3 square root of 11, or 9 square root of 11. And then we have calculate the magnitude of vector OA plus the magnitude, actually it's one single magnitude, so it's vector OA plus vector OB, and we have to calculate the magnitude of that. That means the magnitude of part D, right? So the magnitude of -1, 3, and 1. And this is going to be the square root of 1 plus 9 plus 1, or the square root of 11. So in general, we have that the magnitude of lambda times v is going to equal the absolute value of lambda times the magnitude of vector v. That is, the magnitude of a multiple of a vector is equal to the absolute multiple of the magnitude of the vector. For example, if you have -3 times v, this magnitude would simply equal 3 times the magnitude of v. Now that is because magnitudes are obviously always in positive terms. Also notice that the magnitude of vector OA plus vector OB is not equal to the magnitude of OA plus the magnitude of OB. Because if you do the math, well, we found that this one here is square root of 11. But this other one is going to be different, since the magnitude of vector OA is square root of 38, and the magnitude of vector OB is going to be the square root of 17. So obviously these are not equal. So next we have example 9.2, and it says, find the coordinates of point M in terms of a constant so that points M, A, which is 0, -1, and 5, and B, which is 1, 2, 3, are collinear. So if we want the points to be collinear, it is enough to make vector AM parallel to vector AB. And if two vectors are parallel, we saw that one of them is a scalar multiple of the other. So say AM is equal to T times vector AB. That means that vector AM is going to be, notice that this is going to be, now if we put M, point M, in terms of X, Y, and Z, right? Notice that we're going to get that AM is going to be X, right? That's from X minus 0, so the X minus 0. And then we're going to get that it's Y minus 1, and we're going to get Z minus 5. And this is the same as X, Y plus 1, and Z minus 5. But this is equal to T times vector AB. And vector AB is going to be 1 minus 0, so that's 1. 2 minus minus 1, that's going to be 3. And 3 minus 5, which is going to be negative 2. And if we distribute the t, this is going to be t, 3t, and minus 2t. So in other words, the coordinates of point M in terms of a constant would then be x is equal to t. We get that from here. X is equal to t. Y is equal to 3t minus 1. And z is going to equal 5 minus 2t. So next we're going to take a look at the concept of unit vectors. A vector of length 1 is called a unit vector. In 2D space, for example, I, which is 1 and 0, is going to be the unit vector along the x-axis, and j, which is 0, 1, is going to be the unit vector along the y-axis. In 3D space, you have the same thing with I for x. Notice that it's 1, 0, 0. You can see that vector right here. So it's a vector of 1 unit on the x-axis. And this would be a vector of 1 unit on the y-axis and a vector of 1 unit on the z-axis. These vectors, I, j, and k, are called the base vectors of 3D space. Now, it follows that each vector in 3D space can be expressed uniquely in terms of I, j, and k. So notice that if you have a vector u defined as x, y, z, you can express this as a sum, as you can see here. And this can be rearranged as x times this, y times this, and z times this, which is going to be xi plus yj plus zk. So in general, for example, if you have this vector AB, which we looked at on example 9.1, you can simply express it as 3 times I minus 3 times j minus 9 times k. And if you take a look at figure 9.12, you can have, or you can see an example of u as a sum of multiples of the base vector. So in general, you can represent any vector as the sum of the multiples of the base vectors. Now, unit vectors can be found in any direction, not only in the direction of the axes. For example, if we want to find the unit vector in the same direction as a vector u, then we need to find a vector parallel to u, which has a magnitude of 1. Now, since u has a magnitude of modulus u, if you multiply this vector by this reciprocal, 1 over modulus u, you're going to get a vector of magnitude 1. So the unit vector v in the same direction as u is going to be v is equal to 1 over modulus u times u, which is just u over modulus u. So this is a unit vector of length 1. Now let's take a look at example 9.3, and it says find a unit vector in the direction of v equals I minus 2j plus 3k. So the first thing we would need to do is find the length of this vector. So this is simply going to be the square root of 1 squared plus negative 2 squared plus 3 squared, and this is going to give us square root of 14. Now, all we need to do to find this unit vector is divide v by modulus v. So in other words, 1 over square root of 14 times the vector v, which is I minus 2j plus 3k. And this is obviously just going to give us I over the square root of 14 minus 2 over the square root of 14 times j plus 3 over the square root of 14 times k. Now we can verify to see that this is a unit vector by simply going square root of 1 over square root of 14 and this squared plus negative 2 over the square root of 14 squared plus 3 over the square root of 14 squared, and this is going to give us 1 over 14 plus 4 over 14 plus 9 over 14, and this is obviously going to be 1. In two-dimensional space, we can write the vector in a form that gives us its direction in terms of the angle that it makes with the horizontal axis, called the direction angle, and its magnitude. So if you look at figure 9.13, you're going to see a vector u. The vector u is this whole line, right, from the origin to the ending point. So all of this would be u. Notice that the unit vector v would be u divided by modulus u. V would equal the sum of this vector, which is equal to cosine times I, in this case because it's 1 unit, right? And plus the other vector, which would be sine of theta times j. So the sum of these vectors would give us vector v. Now, if we want to find vector u, notice that rearranging this equation here, we have that u is equal to modulus u times v. In other words, it would be modulus u times cosine of theta times I plus modulus u times sine of theta times j. Notice that this multiplication would extend this vector with a magnitude of u for cosine and the same thing for sine. So in general, we can find a vector in terms of the angle it forms with the horizontal axis by using this simple formula. Now let's focus on example 9.4. And it says, find the vector with magnitude 2 that makes an angle of 60 degrees with the positive x-axis. So this would be 2 times cosine of 60 times I plus sine of 60 j. And this is simply going to be 2 times 1/2 I plus square root of 3 over 2 j. And we end up with I plus square root of 3 j. So next we have example 9.5, and it says find the magnitude and direction of the vector v is equal to 2 square root of 3i minus 2j. So the magnitude is simply going to be modulus v, right? So this is simply the square root of 2 square root of 3 squared plus negative 2 squared. And from here we're going to get square root of 16, which is 4. Now, in order to find the direction, we will need to divide the coefficients here by 4. So notice that we would have that cosine of theta is equal to 2 square root of 3 divided by 4, and this is square root of 3 over 2. And then sine of theta would be minus 2 divided by 4, which is negative 1/2. So notice that from the unit circle, we know that this angle would have to be in the 4th quadrant, with this being negative 1/2, and this distance here being square root of 3 over 2. So obviously the reference angle is 30 degrees. But because it's clockwise, it means it's going to be theta is equal to minus 30 degrees, or in radians, this would be minus pi over 6 radians. So now we continue with example 9.6. And part A says, find the unit vector that has the same direction as v equals I plus 2j minus 2k. So we've done this before. This is just going to be modulus v, which is square root of 1 squared plus 2 squared plus negative 2 squared. And this is going to give us square root of 9, which is 3. So that means that the unit vector u is going to be v divided by 3. So in other words, the unit vector that has the same direction as v is going to be I thirds plus 2/3 j minus 2/3 k. For part B, it says find a vector of length 6 that is parallel to this vector. So that means 6 times the unit vector. From a previous example, example 9.3, we already found that the modulus for this particular vector is square root of 14. So that means that in order to get a vector W with length 6 that is parallel to V, we would have to multiply vector V times 6 over the square root of 14. So this times V, and notice that this is going to give us 6 over square root of 14I minus 12 over the square root of 14j plus 18 over the square root of 14k. So next we have example 9.7, and it says R1 and R2 are the position vectors of 2 points A and B in space, and lambda is a real number. Show that R is equal to 1 minus lambda times R1 plus lambda times R2 is the position vector of a point C on the straight line joining A and B. So for this, let's use an illustration. So notice that the position vector R1 is in reference to A, right? And the position vector R2 is in reference to B. And then there's another vector R that goes to a point C on the straight line joining A and B. So we have to show that this is a position vector. R, so this is part A, R is equal to 1 minus lambda times R1 plus lambda times R2. Okay, so what we're going to do here is rearrange this equation, and notice that we can get that R is equal to R1 plus lambda times R2 minus R1. But R2 minus R1, notice that if I go R2 minus R1, we know that this part here is equal to vector AB. In other words, this is equal to R1 plus lambda times vector AB. But also we can say that R is equal to R1 plus vector AC. And this is equal to what we had before, R1 plus lambda times vector AB. So that means that AC is going to be equal to lambda AB. And that means that AC, or vector AC, is parallel to AB and is a multiple of it. So for part B, they want us to consider the cases where lambda is equal to 0, 1, 1/2, -1, 2, and 2/3. So that means what happens if we substitute, and let's use this formula. R is equal to R1 plus lambda times vector AB. So the question is, what happens when lambda is equal to 0? Well, we're going to get that R is equal to R1. So in that case, we would have that point C would be at A. If lambda is equal to 1, we're going to get that R is equal to R1 plus vector AB. So that means that C would be at B. When lambda is 1/2, we would get that R is equal to R1 plus 1/2 vector AB. So C would be the midpoint of AB. If lambda is equal to -1, then we would have that R is equal to R1 minus vector AB. So that means that A would be the midpoint of CB because point C would be here. Okay, then when lambda is equal to 2, R is equal to R1 plus twice vector AB. So that means that B would be the midpoint of AC because C would be over here. And then finally, when lambda is equal to 2/3, R would be equal to R1 plus 2/3 vector AB. So point C is 2/3 the way between A and B. So C would be somewhere around here.